So here we're going to take a look at so-called coupled substitutions, where atoms going together as a couple instead of a single simple substitution. In what we call the substitutional solid solutions, we had the simple case where we had, let's say, Mg2SiO4 and then Fe2SiO4. So we had the olivine forsterite and then the olivine phthalate, and we're just exchanging a magnesium cation for an iron cation. They have the same charge, and as we show in a prior video, their radii are close enough that we could do pretty extensive exchange. We could do a complete solid solution. We can take magnesium in any kind of, or an iron in any combination we like, and we can write this general formula where we have Mg, Fe2, SiO4 to represent the complete solid solution. So we're just exchanging cations on a single site. Coupled substitution, that means something else. That means we're going to take atoms that come in pairs. So let's say we have the mineral diopside, CaMgSi2O6, and so that is diopside. And then another pyroxene is jadeite, NaAlSi2O6. So that is jadeite. We'll just write that as JD. That's the namesake for the gemstone jade. Here we have calcium as a 2+ cation and sodium as a 1+, so we have a charge mismatch. If we put sodium on the same side as calcium, we lose a charge. How do we gain it? We gain it back by putting an aluminum 3+ in place of the magnesium 2+. So we'll put sodium over here and aluminum over there, and we take care of the charge. The way we can write this is calcium and magnesium go in as a couple and substitute for sodium and aluminum, which also go in as a couple. Notice that the total charge here is 4+, and that maintains charge balance as a 4 with a 4+ couple over here. We can't put in sodium by itself or aluminum by itself, but if we substitute these as a couple, then we maintain charge balance. So we could dissolve jadeite into diopside, where we have a single phase, not two separate pyroxenes, but a single pyroxene phase, and it has a mixture of sodium and calcium and aluminum and magnesium substituting on these respective sites. We do the same thing with the feldspars. So we have CaAl2Si2O8, and in the plagioclase series, that is the mineral anorthite. And then we have NaAlSi3O8, which in the plagioclase series we call albite, or we abbreviate it AN and AB respectively. Again, we have a 2+ charge over here and a 1+ charge over here. The coupled substitution looks something like this. We can have a calcium 2+ and an aluminum 3+ be exchanged for a sodium 1+ and a silicon 4+. Notice that both of these add up to a charge of 5. So if we're going to put sodium into the calcium slot, we also need to add some silicons. So instead of 2 silicons, we'll have 3, and we'll pull out one of the aluminums and put a silicon into a site that would be normally absorbed by an aluminum. And again, that allows us to maintain charge balance. So this is what coupled substitutions are about. Coupled substitutions are a way of maintaining charge balance when we have atoms that fit reasonably well, maybe not perfectly, but well enough to fit in, but the charge balances are not correct. In the simple substitutions, the charges are the same. So if we're going to exchange magnesium for iron, they both have a 2+ charge, so they don't have to go in as a couple with anything else. They can go into the structures individually. But for coupled substitutions, we need to pair up one fellow with another fellow to make sure that we don't gain or lose charge overall in a particular phase.